Hello, I'm Jeffrey Fox, and we're now in the third section of this slide set on going further than Hadoop, which is discussing other systems which pompously we can say manage the global AI modeling supercomputer. Now we come to possibly the most famous, the important Spark, which, if you like, has replaced Hadoop as the darling of the open source systems. It is so useful and powerful and did set some things for the first time very well. Very impressive system built at Berkeley by a group headed by Michael Franklin, who now, by the way, is at the University of Chicago. All right, so here we are. Overview of Spark. If you really want to know more about Spark, there's obviously lots on the web from both the Spark people and other people. We have a slide set from last year solely on Spark, which is much longer than what we have here. But so here we decided not to focus on Spark, but to give this overview of what it takes to build the operating system for the world. Okay. All right, so it's a distributed programming environment, distributed computing system. It is not the fastest, but it probably has more capabilities than anybody else. We don't discuss it in detail, but you could note that Apache Flink, which used to be called Stratosphere, is similar in goals and design. Flink comes from the TU University in Berlin, Europe, and it is pretty competitive. Spark and Flink are both open source as Apache projects, and they both have in-memory cluster computation capability. And they use middleware to allow as much data as possible to be stored in the fast memory. And because of that, it can run much faster than Hadoop in some problems because it's in memory. And even when you use disk, it's faster because it uses it in a cached, powerful fashion. Originally, it started in Scala, although it's always had a Java interface. Now it also has a Python and an R interface. We use, of course, Python and Java as our interfaces to Spark. It has 80 high-level operators, which you can interact with from all these high-level languages. And this number of operators, which is hard to compete with, they're not terribly. Many of them are quite simple, but just 80 is a large number, and we don't have 80 graduate students. And it has various libraries which are greatly important. SQL does what you expect databases, parallel databases, a horizontally scaled parallel database. MLlib is machine learning, a machine learning library. GraphX is graph processing, and Spark Streaming is streaming. Now, the only weakness here is streaming, because its streaming model is not as good as Storm. It is not the same as Storm. It makes streaming as a small batch job, and that's really not what streaming is. And so it's a little surprising they've got away by doing this. Flink, on the other hand, does streaming in the same way as Storm does, as does Twister 2. I'm not quite certain why Spark didn't backtrack and retrofit to do streaming correctly, because their model is just wrong. Although it can do some streaming, can be done that way, it's just not as powerful and accurate as the Storm, Flink, and Twister 2 model. So here we are, 2009. In my defense, I point out I wrote a paper in 2008 in this broad area, which is actually very well cited, but not as well cited as this. And it basically tried to address some difficulties with Hadoop. That disk processing is slow. It only had Java as an application language and no stream processing. And I say, Spark did a marvelous job on the first two and an okay job on the third. And they actually even used it to do streaming applications, Bay Area traffic. And then it became, in 2010, it became open source. In 2013, it became Apache. And now, as I say, possibly the largest Apache project. And now we're up to 2.4. And the version 2.4, that's what our when we look at Spark, that's the version we use. All right. So by using in-memory databases, it decreases the number of reads and write to disks. It also does lazy evaluation. It means it only does things when they're needed. People often define things which are not necessary. We have these operators, which are high-level functions like joins and things like that, which add capabilities. We'll give some examples of operators later on. And they say it can do these other languages, Scala, Python, and R. And of course, Hadoop could actually be used in Scala, Python, and R. It just needs work. We know it takes several months to add Python to Twister 2, which we will be doing over the next few months. The in-memory processing reduces disk reads and writes, which makes everything faster. And the access is immediate. It has a data flow execution engine. Hadoop does not have a data flow execution engine. You'd have to put another system on top of Hadoop to get data flow. It is fault tolerant in a fashion which is much more powerful than Hadoop, because effectively Hadoop just allows you to store the results of the map operators on disk. Spark allows you to form a database called an RDD and write that database to disk. And that disk is written to disk, so it becomes very easy to restart, because you can restart from this RDD, and this RDD has everything you want stored in it, because it's the database of everything important. And I say, streaming certainly does real-time data systems with the limitations I described. It does a range of things which are done separately. It does workflow, because it can spawn and link with the data flow graph different jobs. And that can link machine learning, mapping, and reducing, and queries, and streaming. And it's compatible with all forms of Hadoop data. I mentioned lazy evaluation. And there's a huge community. If you look at the number of meetups and things, Spark has many more than Hadoop. RDDs are very important technology, and I would say the area where they really change the world. And it's a cacheable, then it can be stored in database technology. And this is, if you like, the fundamental data structure. By the way, Storm has a similar data structure. It's called a Streamlit. And Twister 2 has one called a T-set. These database technologies are actually, unfortunately, incompatible. I guess nobody, and I'm sure you could map one into the other, but that's not available at the moment. Basically, an RDD is not an Excel spreadsheet, it's an object. And the object is stored in the distributed fashion, and you can access it in the distributed fashion. And of course, storing objects in memory is much faster than using the network and disks to share. And so that makes iterative processing much better, because Hadoop was terrible at iteration, because every iteration it had to stick everything on disk and restart. So things like k-means clustering, logistic regression, PageRank, they run well in Spark. And they actually run well in Twister 2 and Flink. And then they have technology to automatically join queries together so that they run in an efficient fashion. And I say a key feature, this comes from a database group, and they did a wonderful database, much better than previous people. And other people have learned from what they've done. Twister 2 certainly has learned from what they've done. And you have to, when you write the disk, you're replicating the data, you have to do the I/O, and you have to do the serialization. Spark avoids all of that. It still retains fault tolerance because it does write the disk every now and then. But it does the writing to disk in parallel to whatever else is doing, so the disk is no longer such a bottleneck. All right, so it has transformations. Transformations take one RDD and make a new, and we take one RDD, that's this one, and it's a new RDD, which is this one. And you can actually make one or more RDDs from one input RDD. And you always produce a new RDD. And we all find there's a thing called an action, which takes an RDD and gives you a result. And because RDDs are not useful to the real world, results are useful to the real world. And also there's metadata kept, so you can track the RDDs and how they were created, which helps you do fault tolerance if something crashes. This is called the RDD lineage, or the dependency graph, or the operator graph. And these just describe the transformations that took one RDD and made another. This lineage gives it an execution plan, which allows Spark an efficient execution model. And everything is done with data flow, with directed graphs, and you end up with an RDD, which is the final answer, or maybe multiple RDDs. And then you do an action on that to get the final result. There are types of transformations: narrow or confined to a single partition or node, and wide like shuffle, which cross partitions. Here's some RDD transformations. Remember there were 80. Union, that's a typical database thing. When you want to do partition maps, so you can do general maps. Intersection, find the common elements in RDDs. Find the distinct elements. Do the famous database join. Do a general filter like machine learning. But these are just samples of easy to understand ones. Now you need actions, because action gives you results which you can take and write papers with. And they have actual values, and they execute the RDD graph. And so it's like an RDD operator, but it doesn't produce an RDD. And these are stored either in the controller for the job, which is called a driver, or in an external storage system. And reduce is an action. Collect, which converts RDD to an array of variables. Count, see how many things there are there. These are just actions that anybody would want to use. But so it had another key thing they introduced, which is not new, but is actually new for this type of system. And suddenly when we did our work, we didn't think of this. That's the directed acyclic graph. And this is shown here. Storm has such a graph. Spark has such a graph. It now seems to be recognized as a critical thing to have in these systems. So here we have just things flowing. And this supports this flowing of data through nodes. Nodes are where things happen. That's where RDDs are created and things like that. You can have lots of stages in a DAG, and and the stages basically tell you connected things which can be executed together without changing the processes being used. All right. Notice the links represent the transformations or the operators. These represent the RDDs, essentially, or the actions. We have an important set of libraries: graphs, machine learning, streaming, SQL, R. And you can sort of attribute. You have Spark as the execution engine, and then you add these APIs and functionalities on top of them, like this. So that's a classic architecture, and obviously you can have other things added. The Spark SQL used to be called Shark, but they changed it. Shark is a fancier name, but the trouble is people didn't know it meant SQL, so they changed it to Spark SQL as a better selling name. So you can run Spark with various data sources, HDFS file system, object stores of different types, S3, HBase, Cassandra, any Hadoop data source, and you can run in Mesos, Yarn, or in a standalone fashion without any of these schedulers. And it runs on Amazon EC2, Azure, HPC cluster, etc. Finally, a few comments. It has to have a data system like HDFS, but that's not really a limitation. We want to have a data system like HDFS. It's a rather clumsy big data system, so it doesn't run when there's small amounts of data. MLlib and Spark Streaming are not really the most successful add-ons, and it uses quite a lot of memory. And that may prove to be a problem. So that's Spark, very, very promising critical system. I'm sure you'll be using it in internships and things like that. And I say, this is really not competitive with the many amazing tutorials and also the detailed discussion we gave last year. Thank you very much. The end of the Spark part of this more than Hadoop discussion. Thank you.